Welcome! Today, we're going to solve a system of two equations that looks a bit intimidating at first glance. The system is x to the fifth plus y to the fifth equals 3,126 and x plus y equals 6. Your goal in this video will be to learn how to solve these kinds of problems by recognizing and using specific algebraic identities. The key here isn't to guess and check, but to use algebra. Let's get started. Our first step is to simplify this problem by introducing new variables. This is a common strategy in algebra. Let's define a new variable a as the sum of x and y, and another variable b as the product of x and y. So, we have a equals x plus y, and b equals x times y. The second equation in our system, x plus y equals 6, becomes very simple with this substitution. Since a is x plus y, the equation x plus y equals 6 is now simply a equals 6. We've already found the value of one of our new variables. So, our task now is to find the value of b. To do that, we need to express the first equation, x plus y equals 3,126, in terms of a and b. This might seem complicated, but there's a powerful algebraic identity we can use. The identity we need connects powers of sums. Let's start with a simpler one we might already know. The expression x squared plus y squared can be written as the quantity x plus y squared minus 2xy. In our new variables, that's a squared minus 2b. We can derive this by expanding x plus y squared. It's a fundamental identity. Now let's find an identity for the cubes. We know that x cubed plus y cubed equals the quantity x plus y times the quantity x squared minus xy plus y squared. In our new variables, that's a times a squared minus 2b minus b. This simplifies to a cubed minus 3ab. We could keep deriving these, but for the fifth power, let's use a clever trick. Multiply the identities we already have. Let's multiply our identity for the square by our identity for the cube. Remember that we want to find x to the fifth plus y to the fifth. So we're going to compute the product of x squared plus y squared and x cubed plus y cubed. Distributing this out carefully, we get four terms. X squared times x cubed is x to the fifth. X squared times y squared times x cubed, and y squared times y cubed is y to the fifth. We can rearrange this and factor out a common term from the middle. This gives us x to the fifth plus y to the fifth plus xy squared times the quantity x plus y. Now we substitute in our variables a and b. This means a squared minus 2b times a cubed minus 3ab equals x to the fifth plus y to the fifth plus b squared times a. We can now solve this equation for x to the fifth plus y to the fifth. The result is x to the fifth plus y to the fifth equals a squared minus 2b times a cubed minus 3ab minus ab squared. This is our identity. We've done all the hard work to derive the identity. Now, let's substitute the known values and solve for b. Remember, we know a equals 6, and x plus y equals 3,126. So, our identity becomes 3,126 equals 36 2b times 216 18b minus 6b squared. Let's expand the parentheses on the right side. This gives us 7,776 minus 648b minus 432b plus 36b squared, all minus 6b squared. Now, we combine the like terms, which simplifies the equation. We get 3,126 equals 7,776 minus 1,080b plus 30b squared. This is a quadratic equation for b. We need to rearrange this into standard quadratic form. ax squared plus bx plus c equals 0. By subtracting 3,126 from both sides and simplifying, we get 30b squared minus 1,080b plus 4,650 equals 0. We can divide the entire equation by 30 to get b squared minus 36b plus 155 equals 0. This is the equation we need to solve for b. Now we need to solve the quadratic equation b squared minus 36b plus 155 equals 0. We can do this by completing the square. We rewrite the equation as b squared minus 36b equals negative 155. To complete the square, we take half of the coefficient of b, which is minus 18, and square it, which is 324. We add 324 to both sides of the equation. This gives us the perfect square, b minus 18, squared on the left, and 169 on the right. Now, we take the square root of both sides. The square root of b minus 18 squared is b minus 18, and the square root of 169 is plus or minus 13. Remember to consider both positive and negative roots. This gives us two possible values for b. First, b equals 18 plus 13, which is 31. Second, b equals 18 minus 13, which is 5. We have found the two possible values for b. This means there are two possible scenarios for our original system, which we will now explore. Let's first consider the case where b equals 31. In this scenario, we have a equals 6 and b equals 31. This means x plus y equals 6 and xy equals 31. This implies that x and y are the roots of the quadratic equation t squared minus 6t plus 31 equals 0. To check if there are real solutions, we can look at the discriminant of this quadratic equation. The discriminant, delta, is b squared minus 4ac. In our case, that's 36 minus 4 times 31, which is 36 minus 124, resulting in negative 88. Since the discriminant is negative, there are no real roots, so there are no real solutions for x and y in this case. We can discard this scenario if we're only looking for real solutions. Now let's examine the second case, where b equals 5. Here, a equals 6 and b equals 5. This means x plus y equals 6 and xy equals 5. This tells us x and y are the roots of the quadratic equation t squared minus 6t plus 5 equals 0. The discriminant for this equation is 36 minus 4 times 5, which is 16. Since this is positive, there are two distinct real roots. This means we will find real solutions for x and y in this case. We've confirmed that the case b equals sine 5 will give us real solutions. Now we just need to solve the quadratic equation to find them. Our equation is t squared minus 6t plus 5 equals 0. We can factor this quadratic equation. We need two numbers that multiply to 5 and add up to minus 6. These numbers are minus 1 and minus 5. So, the equation factors into the quantity t minus 1 times the quantity t minus 5 equals 0. This gives us two possible values for t. Either t minus 1 equals 0, which means t equals 1, or t minus 5 equals 0, which means t equals 5. Remember, the roots of this quadratic were our original variables, x and y. So, we have two sets of solutions for our original system. Either x equals 1 and y equals 5, or x equals 5 and y equals 1. Let's check these solutions. It's always a good idea to check our answers with the original equations. Let's check the first solution. X equals 1, y equals 5. The first equation, x plus y equals 6, becomes 1 plus 5 equals 6, which is true. The second equation, x to the 5th plus y to the 5th equals 3,126, becomes 1 to the 5th plus 5 to the 5th, which is 1 plus 3,125, which indeed equals 3,126. So, our solution is correct. The other solution, x equals 5 and y equals 1, will work exactly the same way due to the symmetry of the original problem. We've successfully found the real solutions. So, to recap what we did, we first introduced new variables a and b to simplify the problem. We then used algebraic identities to transform the fifth power equation into an equation in terms of a and b. We solved this new equation, which turned out to be a quadratic for b. Finally, we used the values of a and b to create a new quadratic equation whose roots were the original variables x and y. By following this step-by-step process of simplification and the strategic use of algebraic identities, we were able to solve what appeared to be a very difficult problem. Well done!